So now we know that right angle triangles have three sides that we can give very specific names to. We know that the hypotenuse is the longest side and it's across from the right angle. We also know that there are sides that we call the opposite and the adjacent, and remember that those are relative to the angles that we're dealing with. Okay, so the opposite and the adjacent are going to be different depending on which angle we're talking about. So right now you should have these 8 triangles, either in files or maybe you can print it off. If you can print it off, that's wonderful. Then you should be able to just kind of work through this activity pretty much on your own. It's pretty straightforward. If you don't have it, then I'll invite you to just kind of copy down the numbers that I'm going to put up in a second, or I'll show you guys in a second, of all the measurements of the triangles. You don't need to worry about measuring with a ruler. That's not our outcome. So if you copy down the numbers from my table, that's perfectly fine. Okay, that's not the outcome we're looking for in this lesson. But what I do want you to see on this picture is, whether you're looking at it digitally or you're looking at it kind of in front of you, is there are 8 similar triangles. Okay, and remember, Mr. Neufeld taught you guys all about similar triangles. Similar triangles have the same angle sizes, but their side lengths are different. Their side lengths are in proportion to each other, but they can be different sizes, right? If I took this triangle right here, the one I called number 3, and I kind of expanded it, I could make it the same size as number 4. If I made these O lengths exactly the same, then everything else would be exactly the same, right? They're similar triangles. So you've done a lot of math involving similar triangles, and we're just going to add trig to that, and we're going to show how similar triangles can actually lead us to trig, these trig ratios. And it's actually really cool. So there's 8 triangles. It does not matter which ones you call number 1 or number 2 or number 3. It totally doesn't matter. So I just randomly labeled them from the bottom of my page to the top, which is a perfectly weird way to label triangles, but whatever, it doesn't matter. So you'll notice that on each of the triangles you get an A, an H, and an O. And hopefully by now you can recognize that A stands for adjacent, O stands for opposite, and H stands for hypotenuse. So that implies that these are right angle triangles. Now what this sheet doesn't do is it doesn't put these little boxes in here to indicate that we are actually dealing with right angle triangles. But because it's the hypotenuse, and I didn't make this sheet, I stole it from the internet, we're just going to assume that these are all right angle triangles. And they are, trust me. Now we can do this for any angle size. Normally what we do in the classroom is I give you guys all different angles and then we compare our results to each other. But because we're all in different places right now, it just kind of makes sense for us to look at what happens when 30 degrees is our indicated angle. So if we go back to triangle 1, this angle right here is our indicated angle. This is 30 degrees. That means this angle right here is 60 degrees, right? Because all 3 angles in a triangle need to add up to 180 degrees. Hopefully that's familiar. So we know that this is 30 degrees, and we've got that 30-degree angle, and therefore those 60-degree angles repeated everywhere on this sheet. Okay, so all of these indicated angles are 30 degrees. So what we want to do is we want to measure the lengths of the A's, the O's, and the H's for each of these triangles and put them into the table that looks like this. Okay, so take whichever one you call number 1, it absolutely does not matter. Measure the length of O, A, and H, and then number 2, O, A, and H. You might want to number them though on this paper or check them off or something. If you cannot do that, then because you can't print it off, or if you print it off and it prints off in a different form, I don't know, maybe it gets kind of weird on your printer, I don't know, whatever. If it doesn't work, or these are the measurements I got. Pretty accurate, I think, the best I could do to 1 decimal place for the triangles that I labeled 1, 2, 3, 4, 5, 6, 7, 8. these are the lengths of the opposite, the adjacent, and the hypotenuse, O, A, and H, for each of those triangles. And I measured them in centimeters. And I don't know if you know this, but if you put the unit in the heading of your table, you don't have to write it everywhere else in your table. That unit will apply for everything in the column. So kind of makes things a little shorter and a little neater to work with. So this is the part that you guys need to do on your own. So pause the video, record this down somewhere. It doesn't have to be on this piece of paper. It can be somewhere in your notebook on a piece of loose leaf. But this is the really important stuff. What we want to do is we just want to take our calculator. Here's my calculator. And all we want to do is we want to divide each of these numbers. We want to divide the O, the opposite, divided by the adjacent. So we're just going to take the opposite number. So we have 9.4. So 9.4 divided by, and then the adjacent in this triangle is 16.4 equals, and we just want to write the first 4 decimal places. But I don't want you just to write the 4 decimal places that you see. I want you to round them. Okay, so this guy is decimal 5, 7, 3, and then instead of a 1, because the number that comes after the 1 is a 7, we want to round that up to a 2. Okay, so if I take the length of my opposite and I divide by the length of my adjacent in that triangle, this is the number I get. And it's just a ratio, right? A ratio is really just kind of another way of saying a fraction. That's it. So now let's take a look at the adjacent divided by the hypotenuse. So the adjacent is 16.4 divided by the hypotenuse, which is 18.8. And again, 4 decimal places is really good. Okay, so decimal 8723. Now, I don't know if you were expecting these two numbers to be the same, but think about why it makes sense that they're different numbers, right? We're dividing different, we're dividing 2 totally different numbers. We're getting a different ratio here. So we're not going to see any kind of patterns across the tables, which is my big hint for you guys. But we're definitely looking for patterns kind of throughout. So let's do the last one. Opposite, which is 9.4 divided by the hypotenuse. I get 0.5 on the nose. Oh, well, that makes sense. 9.4 is half of 18.8. Okay, so that makes a lot of sense. Is you want to go through and do those same 3 calculations for each row. Okay, so be really careful that you're not mixing up your numbers, that your opposite and your adjacent get divided in this column, adjacent and hypotenuse get divided in this column, and opposite and hypotenuse get divided in this column. Now, the bottom here asks you to find the average value, and you just need to find the average for that column, this column, and this column. And if in case you don't remember, to find the average or the mean, you add up all of these numbers here and divide by the number of numbers you have. So we're going to have 8 triangles. So we're going to add up all of these numbers here and divide by 8. And we're going to add up all of these numbers and divide by 8 and write the answer here, and add up all these numbers and divide by 8. And that'll tell us kind of what the middle, in case we measured too long or too short. Right, so if the side lengths, we weren't very accurate and maybe in some of our triangles in our measuring, our average hopefully will be a little bit more accurate to what's going on. Okay, so at that point, what I want you to do is I want you to fill this in, and then I want you to send me a message that tells me in your private channel, that tells me what you notice. What did you notice? This is a really, really obvious, really quick thing to notice, but what did you notice when you did these calculations? And if you can extend that just a little bit further and see maybe what on earth do you think it has to do with that 30 degrees? where does that 30 degrees come in? And do you think it would be the same if it was 60 degrees? Or, I don't know, 14 degrees or 27 degrees? Okay, so we want to think about that, and I look forward to reading your postings. All right, great job, guys.